Hi guys, and welcome back to Module 1, Properties and Structures of Matter, and our last inquiry question, which is on bonding. And today we're looking at dipole forces, dipole forces. Now these ones are stronger, permanent electrostatic forces of attraction between the polar molecules. So what's happening in a polar molecule is we have a permanently charged positive and negative end, whereas previously we had, with the dispersion forces, the temporary dipoles. These ones are permanent dipoles there. So the strength of the dipole is directly related then to the melting and boiling points. So if we have a strong dipole, that will obviously be our higher one. So it also depends on the shape of the molecule as well. So with methanol, it's an asymmetrical shape, which leads to being a polar compound, a polar covalent bond, or a polar molecule rather, and its boiling point is minus 19 degrees, whereas ethane, which is a symmetrical shape, is nonpolar and its boiling point is significantly higher. So that means we need to know about our polarity of molecules, and we did this a little bit in class, but we really need to touch on this a little bit more. So to determine the polarity of molecules that have more than two atoms, if it's just two, it's pretty easy to determine if it is polar or not. But when we have a molecule that has more than two atoms, it's a bit more complicated. So it'll depend on the shape of the molecule as well as the polarity of the bonds within the molecule. Now, a general rule tends to be if it's symmetrical, it's nonpolar. If it's asymmetrical, it's polar. So how do we know? We can make those models and have a look at the symmetric nature of that molecule. Of course, also, it's not just dependent on its 2D shape, but its 3D shape. But here is a really good table that helps us a little. So if we have got this type of shape that we've got here, it's an asymmetrical shape. If I have it in 3D, and we'll look at these when you come back to class, it's an asymmetrical shape and therefore it's polar. Our carbon dioxide, where we have our oxygen here and here, they are evenly, the electrons are evenly placed around there. It's the same both ways. It's symmetrical and therefore non-polar. Now, with our tetrafluoromethane here, we have got four fluorine atoms around a central carbon atom. So because of that, it's considered symmetrical. They are four atoms of the same pool, and it's making a non-polar. With water, on the other hand, now in the case of water, while we look in a two-dimensional structure and we can sort of go, oh, it is symmetrical down this line here, because we've got two unpaired electrons either side of the oxygen, it does make for a different type of bonding arrangement and is therefore asymmetrical. So it's often better just to use this table. And in the final case of ammonia that we've got here, despite there being the three hydrogens with that positive dipole and the nitrogen with the negative dipole, similar to what we've got in the fluorine example, the difference here is instead of a bond coming up to our fluorine, again we've got that unpaired electrons, and the pool of electrons is different to the hydrogen that we have down here, so it doesn't create a symmetrical compound. So having a look here in just a different form, here we've got the carbon atom slightly more electronegative, and it's not carbon in this picture. Let's imagine it's methane, so with C and 4 H's. We've got them all 109.5, regardless of whether it is in one dimension or in the other dimension. They are all the same distance apart, so therefore it is considered symmetrical in that 3D view. Looking at polar molecules here, we have got the same shape, for example, the three hydrogens, but in this case here we've got the chlorine up the top, and that chlorine again has different electronegativities, say to the hydrogen, so there is that different pull for those electrons, again creating an asymmetrical shape. And this being the case, it is then that cancels each other out, and so we don't have that symmetrical shape there, and that then affects obviously the polarity of that compound. So what I'm going to get you to do now is go and answer the questions that relate to these 3 types of bonding in your workbook. Talk soon. Bye.